Look up at the night sky, and what do you see? A sea of twinkling lights, each one a star burning bright, some for billions of years, others just a fleeting cosmic moment. But here's the thing no one tells you. Every one of those stars is destined to die, and when they do, their final acts couldn't be more different. Some slip away so quietly, they barely leave a trace, a whisper in the dark. Others go out with a bang so colossal, it ripples through the very fabric of space and time, echoing across dimensions. What decides whether a star's death is a quiet fade or a universe-shaking scream? That's the mystery we're diving into today. Think about it, these aren't just distant lights. They're titanic furnaces, each with its own story, its own fate written in the laws of physics. A star's death isn't random. It's a drama shaped by mass, gravity, and the invisible forces that govern our cosmos. Take our own sun, for example. One day, it'll exhaust its fuel, gently shed its outer layers, and leave behind a glowing ember, a white dwarf fading slowly into the cold. But a star 10 times heavier, that's a different story. Its end is a cataclysm, a supernova so violent it outshines entire galaxies for weeks, leaving behind a black hole, a tear in space-time itself. Why such extremes? What hidden rules decide which stars bow out gracefully and which rewrite the universe on their way out? This isn't just about stars. It's about us too. The iron in your blood, the calcium in your bones, they were forged in these stellar explosions, scattered across the cosmos by dying giants. Every atom in your body was once part of a star's final act. So when we unravel the secrets of how stars die, we're also uncovering the story of our own origins. From the silent fade of white dwarfs to the dimension-defying screams of supernova and black holes, we're about to journey through the most spectacular goodbyes the universe has to offer. Buckle up, this is cosmic storytelling at its most thrilling. To understand why stars die so differently, we need to rewind the cosmic clock, all the way back to their birth. Picture a nebula, a swirling ocean of gas and dust floating in the void. Over millions of years, gravity pulls these particles together, squeezing them tighter and tighter until the pressure at the core ignites nuclear fusion. That's the moment a star is born, lighting up for the first time. But from that very instant, its fate is already sealed, not by chance, but by a single critical factor, its mass. Think of a star's life like a candle flame. A small candle burns steadily, quietly, until it simply runs out of wax. That's how stars like our sun lie, fusing hydrogen into helium in a slow, stable dance that lasts billions of years. But a massive star, it's more like a wildfire burning through its fuel at a furious pace. The bigger the star, the hotter and brighter it shines, but also the shorter its life. And when it finally runs out of fuel, that's when things get explosive. Here's the twist. It all comes down to gravity versus pressure. A star's core is a battleground where these two forces are locked in an endless tug of war. Gravity tries to crush the star inward, while the energy from fusion pushes outward, keeping it balanced. For most of a star's life, this equilibrium holds. But when fusion stops, gravity wins. And how that collapse plays out, whether it's a slow sigh or a universe-shaking detonation, depends entirely on how much mass the star started with. Take a star like our sun. When its fuel runs low, gravity will compress its core into a dense, Earth-sized ember, a white dwarf. Its outer layers will drift away, forming a beautiful but faint planetary nebula. No explosion, no drama, just a quiet fade into cosmic twilight. But a star 8 times heavier, that's when the real spectacle begins. its core collapses so violently that it triggers a supernova, outshining entire galaxies for weeks. And if the star is massive enough, even that explosion isn't the end. The core keeps collapsing, warping space and time until poof, a black hole is born. So the next time you look up at the stars, remember, those tiny points of light are anything but simple. Each one is a ticking clock, a story waiting to end in fire or ice. And the difference between a whisper and a scream, it was written in the stars from the very beginning. But let's zoom in on these quiet cosmic farewells, the ones that don't make headlines like supernova do. Picture a star like our sun, steady and unassuming, burning through its hydrogen fuel for billions of years. It's the definition of cosmic reliability. But even this gentle giant isn't immortal. When it finally nears the end of its life, something extraordinary happens. It swells into a red giant, ballooning to hundreds of times its original size. Imagine Earth's sky filled with a sun so vast it nearly touches our planet. That's the scale we're talking about. This expansion isn't just for show. As the star's core contracts, its outer layers grow unstable, like a pot of water boiling over. Over thousands of years, these layers drift away, forming a glowing shell of gas and dust, a planetary nebula. The name's a bit misleading, though. These nebulae have nothing to do with planets. Early astronomers called them that because their round shapes resemble distant worlds through telescopes. But what they're really seeing is a star's final breath, a slow exhale of stardust lit up by the dying ember at its heart. And that ember, that's the white dwarf, a stellar remnant so dense, a teaspoon of its material would weigh as much as an elephant. Yet despite its incredible mass, it's tiny, barely the size of Earth. For trillions of years, this white dwarf will glow faintly, cooling like a forgotten coal in the cosmic fireplace. No explosion, no drama, just a gradual fade into darkness. What's fascinating is how delicate this process is. A white dwarf exists in a state of quantum defiance, where the pressure of electrons packed tightly together prevents it from collapsing further. It's essentially a cosmic balancing act, a reminder that even in death, stars obey the universe's unbreakable rules. And here's the real kicker. Most stars in the universe, about 97%, will meet this exact fate. The Milky Way is littered with these silent ghosts, the faded remains of stars that once shone like our sun. So why don't we hear more about them? Maybe because they lack the spectacle of their explosive cousins. But there's a quiet beauty in their endings, a reminder that not all cosmic stories need fireworks to be meaningful. In a universe obsessed with extremes, these stars teach us that there's elegance in simplicity, and that sometimes the most profound goodbyes are the ones whispered, not screamed. Now, let's take a closer look at this breathtaking metamorphosis, the red giant phase. Imagine a star like our sun, having spent billions of years burning steadily, suddenly beginning to swell like a balloon left in the sun. Its outer layers expand hundreds of times beyond their original size, turning the star into a colossal, glowing orb. If our sun were to enter this phase today, its outer edges would stretch beyond the orbit of Mars, swallowing Mercury, Venus, and even Earth in a fiery embrace. But this expansion isn't just about size, it's a sign of deep cosmic turmoil. As the star exhausts its hydrogen fuel, its core contracts, growing hotter and denser. Meanwhile, the outer layers grow cooler, giving the star its distinctive reddish hue. The balance that kept the star stable for eons is breaking apart, and the star is now living on borrowed time. And here's where things get even more fascinating. The star doesn't just sit there, burning quietly. It begins to pulse like a heartbeat, growing erratic. These pulsations grow stronger and stronger until the star starts shedding its outer layers in vast, glowing waves. Picture a cosmic onion slowly peeling itself apart, layer by layer. These ejected shells of gas drift outward, illuminated by the intense ultraviolet light still pouring from the star's searing core. That's how planetary nebulae are born, those mesmerizing, ghostly halos we see in telescope images. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, each one tells the story of a dying star's final artistic act. These nebulae aren't just random puffs of gas. They're sculpted by magnetic fields, stellar winds, and even unseen planets, creating intricate shapes that glow in brilliant blues, greens, and reds. What's truly remarkable is how fleeting this phase is. In cosmic terms, planetary nebulae are like fireworks, spectacular but short-lived. Within just tens of thousands of years, the gas disperses, fading into the darkness of interstellar space. All that remains is the star's exposed core, now a white dwarf, still glowing faintly from the heat of its final collapse. So while supernovas steal the spotlight with their explosive drama, the quiet beauty of a planetary nebula reminds us that even the most unassuming stars leave behind something extraordinary. Their deaths aren't just an end, they're a transformation, a final burst of artistry before settling into eternal silence. That dense, Earth-sized ember we call a white dwarf is far more than just a dead star. It's a cosmic time capsule, preserving the final moments of a star's life in incredible detail. Picture taking the entire mass of our Sun and squeezing it into a sphere no bigger than Earth. The result is something so dense, a single sugar cube-sized chunk would weigh as much as an elephant here on our planet. That's the mind-bending reality of a white dwarf's gravity. But here's what's truly fascinating. A white dwarf isn't burning anything. Unlike a living star where nuclear fusion creates light and heat, this remnant survives purely on stored energy, like a hot coal slowly cooling in a fireplace. And when we say slowly, we mean it. A white dwarf takes trillions of years to fade completely, far longer than the current age of the universe. That means every white dwarf we've ever observed is still glowing, still radiating heat from its final collapse. The wildest part, these stellar embers have a built-in limit. Known as the Chandrasekhar limit, this cosmic rule says a white dwarf can't weigh more than about 1.4 times the mass of our Sun. Cross that threshold and gravity wins the battle against quantum pressure, triggering a runaway explosion, a type Ia Supernova. It's one of the most violent events in the universe, so bright it can outshine entire galaxies. But most white dwarfs never reach that point. Instead, they coast silently toward their ultimate fate, becoming a black dwarf. Black dwarfs are the universe's ultimate endpoint for stars like our Sun. Imagine a cold, dark sphere, all its heat and light long since leaked away into space. No fusion, no glow, just a frozen relic drifting through the void. But here's the twist: the universe isn't old enough for any black dwarfs to exist yet. Even the first white dwarfs ever formed are still cooling, still holding onto a faint warmth. It'll take timescales so vast, they make the age of the cosmos seem like a blink before the last white dwarf finally winks out. What's remarkable is how common this silent fate really is. Over 90% of all stars in the Milky Way, including our Sun, are destined to become white dwarfs. That means most stars won't go out with a bang, but with a slow, steady dimming. There's something almost poetic about that. While the universe celebrates the explosive deaths of massive stars, the humble white dwarf reminds us that quiet endings have their own beauty, a gradual fade into the cosmic background, leaving behind only gravity and memory. And yet, even in their silence, white dwarfs have stories to tell. Their atmospheres are like stellar autopsies, revealing traces of elements that once floated in their outer layers. Some are polluted with the remnants of shredded planets, evidence of entire worlds torn apart by the star's immense gravity. Others pulse faintly, their surfaces vibrating like struck bells, giving astronomers a way to peer deep into their interiors. These silent sentinels might not scream across the cosmos, but they whisper secrets of stellar life and death to those who know how to listen. Even the quietest stars can rebel against their fate if given the chance. Take white dwarfs, those fading embers of sun-like stars. Most will cool silently into oblivion, but some have a far more explosive destiny waiting. It all hinges on a cosmic tipping point called the Chandrasekhar limit, named after the astrophysicist who discovered it. This critical threshold, about 1.4 times the mass of our Sun, is the difference between a slow fade and a spectacular cosmic detonation. Here's how it happens. Imagine a white dwarf in a binary system orbiting another star like a silent predator. Over time, its immense gravity can siphon material from its companion, growing heavier and heavier. At first, this stolen mass just makes the white dwarf denser, compressing its core to unimaginable pressures. But cross that 1.4 solar mass line and everything changes. The core can no longer support its own weight. Carbon atoms, once stable, suddenly begin fusing in an uncontrollable chain reaction. In less than a second, the entire white dwarf becomes a bomb, a type Ia supernova. What makes these explosions so extraordinary is their consistency. Unlike other supernovae, which vary wildly in brightness, type Ias always release nearly the same amount of energy. That's because they ignite at almost identical masses, like precision-engineered fireworks. Astronomers call them standard candles, cosmic lighthouses so reliable, we use them to measure distances across the universe. When one erupts, it can outshine its entire host galaxy for weeks, visible halfway across the observable cosmos. But the real magic lies in what these explosions leave behind. Unlike massive stars that collapse into black holes or neutron stars, a type Ia supernova obliterates itself completely. No remnant, no corpse, just an expanding cloud of heavy elements like iron, gold, and uranium scattered into space. That's right, the gold in your jewelry likely came from a white dwarf's final, fiery act billions of years ago. There's a cosmic irony here. White dwarfs spend eons as the universe's most orderly objects, cooling with quiet dignity. Yet, given just a little too much mass, they become agents of chaos, forging the very elements that make planets and life possible. It's a reminder that in the cosmos, even the quietest players can rewrite the story when the conditions are right. And sometimes the most silent stars leave the loudest echoes. Massive stars don't just burn, they rage. From the moment they ignite, these celestial titans wage a war against their own gravity, fusing elements at a pace that would make smaller stars shudder. Take a star 20 times heavier than our Sun. Its core burns so hot and so fast that it tears through its hydrogen fuel in just a few million years, a cosmic blink compared to the Sun's 10 billion-year lifespan. But that speed comes with a price. The heavier the star, the more extreme its fate. Deep in the heart of these giants, nuclear fusion isn't just a slow burn, it's a frantic sprint. Hydrogen fuses into helium, helium into carbon, carbon into neon, and so on, each reaction cramming heavier elements into the core like layers of a cosmic onion. By the time silicon starts fusing into iron, the star's days are numbered. Iron is the universe's nuclear dead end. Unlike lighter elements, fusing iron doesn't release energy, it sucks it up. And that's when the star's delicate balancing act collapses. Literally, in a fraction of a second, the core, no longer supported by outward pressure, implodes. Protons and electrons crush together so violently they form neutrons, releasing a flood of neutrinos. The outer layers, suddenly without a foundation, come crashing down at a quarter the speed of light until they hit the neutron core and rebound in the most violent shockwave imaginable. That rebound is the supernova, an explosion so bright it can outshine entire galaxies. For weeks, it floods the cosmos with light, hurling newly forged elements like gold, uranium, and platinum into space. But the aftermath is just as astonishing. Depending on the star's mass, the core might survive as a neutron star, a city-sized object so dense, a single teaspoon weighs 1 billion tons. Some spin rapidly, beaming radiation like cosmic lighthouses. We call those pulsars. Others have magnetic fields strong enough to rip atoms apart, and if the core is heavy enough, it collapses past the point of no return, warping space-time into a black hole. What's truly humbling is how these explosions shape the universe. Every breath you take contains oxygen forged in a dying star's final moments. The calcium in your bones, the iron in your blood, they were all scattered across space by supernova. These violent endings aren't just destruction, they're creation. Without them, planets and life wouldn't exist. So while massive stars may live short, fiery lives, their deaths are the reason the cosmos is more than just hydrogen and helium. They're the alchemists of the universe, turning stardust into the building blocks of everything we know. Picture a single star 20 times more massive than our sun, reaching the end of its life. Deep in its core, fusion has been racing like a runaway train, forging heavier and heavier elements until only iron remains, and iron is the universe's ultimate betrayer. Unlike every element before it, iron doesn't release energy when fused, it steals it. In an instant, the star's delicate balance shatters. The core, no longer able to resist gravity's pull, collapses at nearly a quarter the speed of light. Then boom, the rebound shockwave tears through the star with unimaginable force, unleashing a supernova so bright it can outshine 1 billion suns. This isn't just an explosion. It's a cosmic forge. The temperatures inside a supernova are so extreme, billions of degrees, that atoms are smashed together, creating elements heavier than iron. Gold, platinum, uranium, the very metals that make up our electronics, our jewelry, even parts of our bodies, were born in these cataclysmic detonations. The explosion hurls them outward at incredible speeds, scattering them across interstellar space like seeds. Over millions of years, those atoms will drift into clouds of gas and dust, eventually becoming part of new stars, new planets, and perhaps even new life. But the shockwaves don't stop there. A supernova's energy is so immense, it doesn't just light up the cosmos, it bends it. The explosion sends ripples through space-time itself, disturbances so subtle we've only recently learned to detect them. These gravitational waves, as they're called, travel across the universe, carrying with them the echoes of a star's final scream. When two black holes or neutron stars collide, the waves they produce are strong enough for us to measure. But even a supernova's faint tremors, like whispers in the fabric of reality, tell us something profound. Death for a massive star isn't an end. It's a transformation that echoes across dimensions. And here's the wildest part. We owe our existence to these explosions. Every atom in your body heavier than hydrogen and helium was forged in the heart of a dying star. The oxygen you breathe, the calcium in your bones, the iron in your blood, they were all scattered into space by supernova billions of years ago. Without these violent endings, the universe would be a sea of simple elements with no planets, no chemistry, no life. So the next time you look up at the night sky, remember, those distant points of light aren't just stars. They're future supernova, future creators, the cosmic alchemists turning stardust into everything we know. Core collapse supernova are the universe's grandest finales, cosmic fireworks so powerful they can outshine entire galaxies. Imagine a star so massive it makes our sun look like a speck. For millions of years, it burns furiously, fusing elements in a desperate race against gravity. But when its core finally fills with iron, the star's fate is sealed. Iron is fusion's dead end. It absorbs energy instead of releasing it. In an instant, the core's outward pressure vanishes, and gravity takes over with terrifying force. What happens next is almost unimaginable. The core, packed with the mass of several suns, collapses at nearly a quarter the speed of light. Protons and electrons are crushed together, forming a solid ball of neutrons. Then, like a spring recoiling, the outer layers slam into this ultra-dense core and rebound in a shockwave so violent, it rips the star apart. The explosion releases more energy in seconds than our sun will in its entire lifetime, lighting up the cosmos with a brilliance visible across the universe. But the drama doesn't end there. The core's fate hinges on a cosmic tipping point. If it's between about 1.4 and 3 times the sun's mass, it becomes a neutron star, an object so dense, a single sugar cube of its material would weigh 1 billion tons on Earth. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like lighthouse beams. These are pulsars, nature's most precise clocks. Others, called magnetars, have magnetic fields trillions of times stronger than Earth's, capable of ripping atoms apart from thousands of miles away. And if the core is even heavier, gravity wins completely. The collapse doesn't stop at neutrons, it warps spacetime itself, forming a black hole. Not even light can escape its pull. What's left behind is a gravitational monster, surrounded by the scattered remains of the star's outer layers, now enriched with heavy elements forged in the explosion's fury. This isn't just destruction, it's creation. The gold in your jewelry, the uranium in nuclear reactors, even the iodine in your thyroid, all were forged in these violent stellar deaths. Without core collapse supernova, the universe would lack the ingredients for planets, for life, for us. So while these explosions mark the end of a star's story, they're also the beginning of countless others, scattering stardust across the cosmos like seeds waiting to grow. When a massive star collapses in a supernova, sometimes the universe doesn't just leave behind a black hole. It creates something equally strange but far more visible. Meet the neutron star, nature's most extreme physics experiment. Picture squeezing 1.5 times the mass of our sun into a sphere no wider than Manhattan. The result is so dense, a single sugar cube of its material would outweigh Mount Everest. That's not science fiction, that's real cosmic alchemy at work. These stellar zombies are born from chaos. During a supernova, the core's collapse is so violent that protons and electrons get crushed together, forming a solid ball of neutrons. No empty space exists between atoms here, just neutrons packed tighter than sardines in a can. The gravitational pull at the surface is 200 billion times stronger than Earth's. Drop a marshmallow from just 1 meter above, and it would hit the surface with the energy of a nuclear bomb. But neutron stars aren't just dense, they're also cosmic dynamos. Many spin hundreds of times per second, faster than a kitchen blender. As they rotate, their insane magnetic fields trillions of times stronger than Earth's channel radiation into narrow beams. When these beams sweep past Earth like a lighthouse, we call them pulsars. The Crab pulsar, born in a supernova observed in 1054, still spins 30 times every second, flashing so predictably we could set atomic clocks by it. Then there are magnetars, neutron stars on cosmic steroids. Their magnetic fields are so powerful, they'd erase every credit card on Earth from halfway across the solar system. In 2004, a magnetar 50,000 light-years away released a burst of energy that briefly outshone the full moon, despite being far beyond our galaxy. These monsters can crack their own surfaces in starquakes, releasing flares that rewrite what we thought possible about magnetic fields. What's truly mind-blowing is how these dead stars influence the living universe. Colliding neutron stars create gravitational waves we can detect, and in 2017, such a collision gave us proof they forge gold and platinum. The ring on your finger likely contains atoms born in a neutron star's final death throes. So while black holes steal the spotlight, neutron stars remind us that sometimes the most fascinating cosmic stories come from objects that refuse to fade quietly into the dark. Black holes aren't just the end of a star's life, they're a cosmic paradox, a place where the laws of physics as we know them break down completely. Picture the core of a star so massive that not even the fierce pressure of neutrons can stop its collapse. Gravity wins utterly, crushing matter into a point of infinite density, a singularity. Around it, an invisible boundary forms, the event horizon, the point of no return where even light speed isn't fast enough to escape. Cross that line and there's no coming back. What makes black holes so terrifying and fascinating is how they warp the very fabric of reality. Space and time aren't just bent here, they're twisted into knots. Get too close and time slows to a crawl relative to the outside universe. A single minute near the event horizon could mean years passing elsewhere. And if you were to fall in, the tidal forces would stretch you into a strand of atoms in a process physicists grimly call spaghettification. But here's the twist: from your perspective, nothing unusual might happen until it's too late. That's the eerie beauty of relativity. Yet black holes aren't just destroyers, they're creators too. When a supermassive star collapses, the explosion hurls heavy elements into space, seeding future generations of stars and planets. And the black hole itself, it becomes a gravitational anchor shaping galaxies around it. At the heart of nearly every large galaxy, including our Milky Way, lurks a supermassive black hole, millions or even billions of times heavier than our Sun. These monsters didn't form from single stars, they grew over eons, swallowing gas, dust, and even other black holes in a slow cosmic feast. Then there's the sound. Not literal sound, of course, space is silent, but the ripples black holes send through spacetime itself. When two black holes spiral toward each other, their collision shakes the universe, sending out gravitational waves. These waves, first detected in 2015, are like echoes of a scream across dimensions, proof that even the most violent cosmic events leave traces we can decode. Perhaps the most mind-bending part, black holes might not last forever. Thanks to quantum effects near the event horizon, they slowly leak energy, a phenomenon called Hawking radiation. Over trillions upon trillions of years, even the mightiest black hole could evaporate into nothingness. But that's the far future. For now, they remain the universe's most enigmatic predators, silent shadows that remind us. Some stars don't just die, they transform into something beyond our wildest imagination. If supernova are the universe's fireworks, then hypernova are its nuclear detonations, stellar explosions so powerful they dwarf everything else in the cosmos. Picture a star not just 20, but 50 or even 100 times heavier than our Sun. When these behemoths reach the end of their lives, they don't simply collapse, they implode with such apocalyptic force that the explosion becomes a cosmic spotlight, visible clear across the observable universe. This is a hypernova, a supernova's bigger, meaner sibling, capable of unleashing energies that defy comprehension. At the heart of these cataclysms lies something even more extraordinary: gamma-ray bursts. These are the universe's most powerful electromagnetic explosions, jets of radiation so intense they can outshine 1,000,000,000,000,000 suns for a few fleeting seconds. Born from the chaotic collapse of hypermassive stars or the collision of neutron stars, these beams of pure energy slice through space like cosmic lasers. If one were to hit Earth from even a few thousand light years away, it could strip our ozone layer, triggering mass extinctions. Thankfully, the nearest candidates are billions of light years distant, but their sheer power reminds us how small we are in the grand scheme of things. What makes these events so mind-bending is how they warp physics itself. As the star collapses, its core doesn't just form a neutron star or black hole. It funnels the explosion's energy into twin jets, blasting outward at nearly the speed of light. These jets, packed with gamma rays and charged particles, punch through the star's outer layers like bullets through tissue paper. When we detect a gamma-ray burst, we're essentially seeing a death scream focused into a beam narrower than a pencil's tip, yet bright enough to pierce the cosmos. The aftermath is just as astonishing. Hypernova forge elements heavier than iron in quantities no ordinary supernova could match. The gold in your jewelry, the platinum in catalytic converters, much of it was likely forged in these rare, ultra-violent explosions. And the black holes they leave behind, some spin so fast they warp space-time into a vortex, dragging nearby matter into a swirling disk of superheated plasma that glows brighter than entire galaxies. Yet for all their destructive potential, hypernova and gamma-ray bursts are cosmic architects. They seed galaxies with heavy elements, shock clouds of gas into forming new stars, and even, theoretically, create the conditions for exotic phenomena like magnetars. In a universe where most stars fade quietly, these titanic explosions remind us that some endings aren't just finales, they're the birth cries of new cosmic eras. Imagine a star so colossal, so unimaginably massive, that its own heat becomes its executioner. We're talking about stars over 100 times heavier than our sun, cosmic leviathans that live fast, burn furious, and die in one of the most spectacular ways the universe has to offer. This isn't just a supernova, this is something far more extreme, a pair-instability supernova, where the star doesn't just collapse or explode, it completely annihilates itself from the inside out. Here's how this cosmic self-destruction unfolds. Deep in the core of these hypermassive stars, temperatures reach staggering highs, billions of degrees. At these extremes, something bizarre happens. The energy becomes so intense that it spontaneously creates pairs of particles and antiparticles, like electrons and positrons, right out of thin air. Normally, a star's core is held up by the outward pressure of nuclear fusion, but this sudden creation of matter and antimatter saps that energy away. It's like pulling the floor out from under a building. The core loses pressure and gravity immediately takes over, triggering a runaway collapse. But here's where things get wild. As the core implodes, temperatures skyrocket even further, so high that oxygen and silicon begin fusing explosively. This isn't the controlled burn of a normal star. It's a thermonuclear detonation of unimaginable scale. The energy released doesn't just blow off the outer layers, it completely obliterates the star, leaving no black hole, no neutron star, not even a wisp of a remnant behind. The entire star is torn apart in a blast so powerful, it can outshine an entire galaxy for weeks. What's truly mind-bending is how rare these events are. Pair-instability supernova require such specific conditions that they likely only happened in the early universe, when stars grew to these monstrous sizes. Today, with fewer raw materials floating around, stars rarely reach such extremes. but when they do, their deaths are so violent, they literally erase themselves from existence. And here's the cosmic irony: these explosions are so thorough, they leave nothing behind. No heavy elements trapped in a black hole, no dense neutron star spinning in the void. Just an expanding cloud of gas, rich with newly forged elements scattered across the cosmos. In a universe where most stellar deaths create something new, a white dwarf, a pulsar, a black hole, pair-instability supernova are the ultimate vanishing act. One moment, a star of impossible scale; the next, nothing but light fading into the endless dark. In the cosmic dance of stellar life and death, some stars refuse to follow the script. While most fade quietly or explode spectacularly, others find bizarre ways to cheat the reaper, entering twilight states that defy all expectations. Take the Thorn-Zitkow object, a theoretical monster that sounds like something from a sci-fi novel. Picture a neutron star, the dense corpse of a supernova swallowed by the bloated belly of a red giant. These two stellar extremes shouldn't coexist, yet under the right conditions, the neutron star orbits inside its massive host like a parasitic core, warping the giant's fusion processes. The result, a star within a star, burning unusually heavy elements like rubidium and lithium in its outer layers, chemical fingerprints that could betray these cosmic oddballs to astronomers. Then there are the vampire stars, not Hollywood fantasies, but real celestial predators. In binary systems where one star ages faster than its companion, the dying star can siphon fresh hydrogen fuel from its neighbor, effectively stealing its youth. This stolen material reignites fusion in the aging star's outer layers, giving it a second wind that prolongs its life far beyond its natural lifespan. The donor star, now drained and dimmer, orbits its revived partner like a ghost of its former self. It's a cosmic case of survival at someone else's expense. But perhaps the strangest undead stars are the ones that refuse to die quietly, like magnetars. Born from supernova, these neutron stars don't just fade into obscurity. Their unimaginably strong magnetic fields, quadrillions of times more powerful than Earth's, crack their own surfaces, releasing bursts of energy that can disrupt radio signals across the galaxy. For years, astronomers puzzled over mysterious deep space flares until they realized these were the death throes of stellar corpses, refusing to go gently into that good night. What unites these stellar zombies is their defiance of simple endings. They blur the line between life and death, proving that in the cosmos, even the most extreme rules have exceptions. Whether it's a neutron star hiding inside a giant or a vampire draining its companion, these outliers remind us that the universe loves a good plot twist, and that death for stars isn't always the end of the story. Among the universe's most terrifying objects, magnetars stand out as cosmic anomalies. Neutron stars turned up to 11. Imagine taking the mind-bending density of a neutron star and cranking its magnetic field to levels that defy logic, a quadrillion times stronger than Earth. To put that in perspective, if a magnetar floated halfway between Earth and the Moon, its magnetic pull would erase every credit card on the planet, not by hacking but by sheer physics. These aren't just dead stars, they're celestial monsters with the power to warp reality itself. What makes magnetars so volatile? It all comes down to their birth. When an especially massive star goes supernova, its collapsing core doesn't just form a neutron star, it twists. The chaotic turbulence of that collapse, combined with the star's rapid rotation, amplifies its magnetic field to unimaginable levels. Picture a dynamo the size of a city, spinning faster than a blender and wrapped in magnetic lines so intense they could rip atoms apart from thousands of miles away. That's a magnetar, a ticking time bomb of cosmic energy, and when these bombs go off, the universe notices. magnetars don't fade quietly, they crack literally. The unimaginable stress of their magnetic fields can fracture their own crusts in violent starquakes, releasing flares of gamma rays and X-rays brighter than 100 suns. In 2004, a magnetar 50,000 light-years away unleashed a burst so powerful, it temporarily ionized Earth's upper atmosphere despite being far outside our galaxy. For a fraction of a second, this stellar corpse outshone the full moon, proving that even in death, some stars refuse to be ignored. Yet magnetars aren't just destroyers. Their extreme physics offers scientists a laboratory for testing the universe's most bizarre rules. Take magnetic reconnection, where twisted field lines snap and realign, releasing enough energy to power a star for centuries. On the Sun, this process triggers solar flares. On a magnetar, it could vaporize a planet, and then there's their spin. Some rotate once every few seconds, while others whirl at a dizzying 1,000 times per second, their surfaces moving at a significant fraction of light speed. Perhaps the most haunting detail, magnetars are fleeting. Those insane magnetic fields decay over time, and within 10,000 years, a blink in cosmic terms, they fade into ordinary neutron stars. But while they last, they remind us that the universe has a flair for drama. Whether it's a starquake shaking the galaxy or a magnetic pulse rewriting physics textbooks, magnetars prove that some stars don't just scream into the void, they roar. In the cosmic theater of stellar explosions, not every bright flash is a final curtain call. Meet the universe's greatest deceivers, supernova imposters. These dazzling eruptions mimic the violence of a true supernova, lighting up the cosmos with enough brilliance to fool even seasoned astronomers. But here's the twist: the star survives. Unlike their catastrophic counterparts, these outbursts are cosmic performances, a star's way of shedding layers without meeting its end. Take Eta Carinae, one of the Milky Way's most enigmatic stars. In the 1840s, it unleashed the Great Eruption, a tempest so violent it ejected enough material to build 10 suns. For over a decade, it outshone every star in the galaxy except Sirius, despite being 7,000 light-years away. Telescopes today still capture the aftermath, the homunculus nebula, a glowing hourglass of gas and dust flung outward by the star's tantrum. Yet, against all odds, Eta Carinae still burns. What fuels these bizarre near-death experiences? The answer lies in instability. Supermassive stars like Eta Carinae walk a razor's edge, their outer layers so loosely bound that radiation pressure can overpower gravity. When the star's core heats up excessively, it doesn't trigger collapse, it triggers expulsion. The star essentially coughs off its outer layers in a series of violent spasms, like a volcano erupting in slow motion. These outbursts can recur over centuries, leaving the star diminished but very much alive. The universe loves a good gray area, and supernova imposters are the ultimate proof. They challenge our neat categories of stellar life and death, showing that stars don't always choose between a whisper and a scream. Sometimes they opt for a roar that doesn't end them, a celestial mic drop that leaves everyone guessing what comes next. What's truly fascinating is how these events rewrite stellar evolution. A single imposter eruption can strip away years of a star's lifespan, altering its future explosions or even preventing a supernova entirely. Some theorize that Eta Carinae's next act might be a hypernova, or it might fizzle into a quiet demise. The unpredictability is what makes these stars so compelling. They're cosmic wildcards, reminding us that the universe's rulebook always has room for surprises. So the next time a star lights up the night sky, don't assume it's a farewell. It might just be the universe's way of keeping us on our toes, proving that even in the vastness of space, drama doesn't always end with a bang or a whimper. but with an encore no one saw coming. We think of stars as cosmic engines governed by pure physics, hydrogen fusing into helium, gravity battling pressure, mass dictating fate. But what if there's an invisible player in this drama? Enter dark matter, the universe's most elusive substance. It doesn't emit light, doesn't interact with ordinary matter, yet it outweighs everything we can see by 5 to 1. And some scientists suspect it might be pulling strings in stellar life cycles, quietly shaping how stars live and die. Here's the tantalizing idea. Dark matter particles drifting through space could accumulate inside stars over billions of years. Unlike normal matter, they wouldn't get caught up in fusion or radiation, they'd just linger. In small stars like our Sun, this might not matter much. But in massive stars or dense stellar environments like galactic centers, the buildup could be significant. Picture trillions of these ghostly particles clustered in a star's core, subtly altering its internal dynamics. They might act like invisible weights, speeding up fuel consumption or destabilizing the delicate balance between gravity and pressure. The implications are staggering. If dark matter shortens a massive star's lifespan, it could trigger supernova earlier than expected. Or, in some cases, it might sap energy from the core, causing a star to collapse into a black hole without the usual fireworks. Even white dwarfs, those quiet stellar embers, might be affected. Some theories suggest dark matter could provide just enough extra heat to reignite fusion on their surfaces, leading to unexpected explosions. Then there's the galactic wild card, dark matter's uneven distribution. Stars born in regions thick with dark matter, like the Milky Way's halo, might evolve differently than those in emptier spaces. Imagine two identical stars, one in a dark matter-rich zone, the other not. The first could burn hotter, die younger, or even collapse into a black hole while its twin fades peacefully. It's a cosmic version of nature versus nurture, with invisible matter playing the role of silent puppeteer. Of course, this is all theoretical. Detecting dark matter's influence on stars is like trying to spot a shadow in a pitch-black room. But astronomers are hunting for clues. Some study unusual supernovae that defy expectations, searching for anomalies that dark matter might explain. Others model how these particles could alter stellar cores, simulating their effects down to the quantum level. What's thrilling is the possibility that dark matter isn't just out there, it's in the stars themselves, shaping their destinies in ways we're only beginning to imagine. If proven true, it would rewrite stellar physics, revealing that the universe's greatest mysteries aren't just around us, but burning inside the very hearts of the stars we thought we understood. When two black holes spiral toward each other in a cosmic dance of death, they don't just vanish into the darkness, they shake the universe itself. These cataclysmic mergers send ripples racing through space-time at the speed of light, distorting the very fabric of reality like a stone dropped in a pond. These are gravitational waves, the universe's most subtle yet far-reaching messengers, carrying secrets from collisions that happened billions of years ago. Einstein predicted their existence over a century ago, but it wasn't until 2015 that humanity first detected them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the faint whisper of two black holes merging 1.3 billion light-years away. The signal lasted just 0.2 of a second, but in that heartbeat of time, it confirmed that stars don't just die in place. Their final moments can reverberate across dimensions, warping space-time itself. What's astonishing is how delicate these distortions are. The waves from that first detected collision stretched and squeezed Earth by 1,000th the width of a proton. To measure such microscopic changes, LIGO uses lasers traveling down 4-kilometer-long vacuum tubes, bouncing between mirrors so precisely suspended that they're isolated from earthquakes, passing trucks, even the rumble of ocean waves. That's how quiet the universe's loudest screams really are, yet their implications are anything but small. Every gravitational wave carries a forensic record of its origins. The pattern of the ripples reveals whether the collision involved black holes or neutron stars, their masses, even how fast they were spinning. Some waves sound like a rising chirp as the objects spiral closer, ending abruptly when they merge. Others, like the one from two neutron stars colliding in 2017, came with an electromagnetic fireworks show, gamma rays, X-rays, even visible light, proving these events forge heavy elements like gold and platinum. What's truly humbling is how these waves transcend dimensions we can't perceive. Just as sound travels through air, gravitational waves propagate through the higher dimensions predicted by string theory, making them our only window into realms beyond length, width, and height. When LIGO detects a wave, we're not just hearing a star's death, we're eavesdropping on the hidden geometry of the cosmos. So while supernova light up telescopes and black holes lurk invisibly, gravitational waves remind us that the most profound cosmic events aren't always seen or heard in conventional ways. Some stars leave their mark not with light or matter, but by bending the stage upon which the universe plays out. A final, multidimensional scream etched into space-time itself. At the heart of every stellar explosion and every silent fade lies a hidden quantum drama. While stars may seem like titanic objects governed solely by gravity and fusion, their ultimate fates are often decided by rules so small they defy imagination. Take neutron stars, those city-sized remnants of supernova. Their very existence is a quantum miracle. When a massive star collapses, gravity tries to crush its core into oblivion. But just before it succeeds, something extraordinary happens. The particles inside get packed so tightly that quantum mechanics takes over. Electrons and protons merge into neutrons, and suddenly, an invisible force called neutron degeneracy pressure pushes back. It's not like normal pressure, it's not heat or motion holding the star up. It's the sheer refusal of subatomic particles to occupy the same state, a quantum rebellion against gravity's pull. This same quantum defiance shapes white dwarfs too. These Earth-sized embers of sun-like stars are held up by electron degeneracy pressure, a similar quantum rule where electrons, squeezed beyond reason, push back like a crowd refusing to be crammed into a shrinking room. But here's where quantum mechanics shows its fangs. There's a limit to how much pressure electrons can muster. Cross it by adding just a bit more mass, and even quantum laws can't save the star. The electrons get crushed into protons, forming neutrons, and the white dwarf collapses into a neutron star or explodes as a supernova. That tipping point, the Chandrasekhar limit, isn't just a number, it's a quantum boundary between a quiet fade and a cosmic cataclysm. Then there are black holes where quantum mechanics and gravity wage their ultimate war. At a black hole's singularity, all known physics breaks down. Matter is crushed to infinite density, space and time twist into knots, and our equations dissolve into nonsense. Yet even here, quantum effects leave fingerprints. Stephen Hawking predicted that black holes aren't perfectly black. They slowly leak energy, evaporating over eons due to quantum fluctuations near the event horizon. It's a paradox. The universe's most destructive objects might ultimately vanish in a whisper of particles, all because of quantum uncertainty, the strangest part. These microscopic rules shape the cosmos on the grandest scales. Without neutron degeneracy pressure, neutron stars wouldn't exist. No pulsars, no magnetars, no gravitational waves from their collisions. Without electron degeneracy, white dwarfs would collapse quietly, leaving no spectacular supernova to seed the universe with heavy elements. Even the gold in your jewelry owes its existence to quantum mechanics. The very rules that govern particles smaller than atoms also decide whether a star's death creates or destroys. So the next time you look at the night sky, remember, those distant lights aren't just governed by gravity's pull. Their fates and ours are written in the quantum fine print, where the tiniest laws have the largest consequences. Not every cosmic object gets the luxury of a dramatic exit or even a quiet fade. Some are sentenced to an eternity of silence, not with a whisper, but with none at all. Meet rogue planets, celestial orphans cast adrift in the interstellar dark, untethered from any star, any light, any warmth. These lonely wanderers don't just represent stellar death, they embody its most chilling aftermath, a fate where even the faintest cosmic murmur fades into absolute stillness. Picture a planet like Jupiter, born in the swirling disk of a young star system. For millions of years, it orbits dutifully, until a gravitational tug of war with neighboring giants flings it into the abyss. Suddenly, it's hurtling through space at hundreds of thousands of miles per hour, its atmosphere freezing solid as the distant glow of its former sun shrinks to a pinprick, then vanishes entirely. No sunset, no dawn, just an endless midnight where temperatures plunge near absolute zero. This isn't science fiction. Astronomers estimate there could be billions of these rogue planets drifting through our galaxy alone, invisible to telescopes unless they pass directly in front of distant stars. What's haunting about these worlds isn't just their isolation, it's what they carry with them. Some might still cling to thick hydrogen atmospheres, frozen into exotic ices we've never seen on Earth. Others, ejected early in their system's chaos, could harbor vast subsurface oceans kept liquid by radioactive decay or tidal friction, their icy crusts sealing away potential habitats in perpetual darkness. Imagine life evolving around hydrothermal vents in these lightless seas, never knowing a sky exists, its entire universe bounded by ice and rock. Yet the true silence of rogue planets lies in their imperceptibility. Unlike white dwarfs or neutron stars, they leave no glowing remnants, no shockwaves, no gravitational ripples. They are cosmic ghosts, their presence detectable only by the subtlest distortions in starlight, if at all. While stars scream or whisper their deaths, these planets simply vanish, slipping into the void without a trace. But here's the twist: some rogue planets might not stay silent forever. Collisions between these wanderers, though rare, could ignite brief flashes in the darkness, a momentary crack of light as frozen atmospheres combust or icy surfaces shatter. Others, captured by new stars billions of years later, might thaw into bizarre hybrid worlds, their chemistry forever altered by eons of deep freeze. In the end, rogue planets remind us that the universe's quietest fates aren't about how something ends, but how it persists. They are the unchronicled stories, the unseen majority, drifting through a cosmos too vast to notice their passing. And in their endless journey, they pose a humbling question: is it lonelier to die with a whisper or to wander forever unheard at all? Every supernova remnant, every glowing nebula, every silent white dwarf is like a page in the universe's history book, written not in ink but in light, gravity, and elemental fingerprints. This is stellar archaeology, the science of reading the last words of dead stars to reconstruct cosmic events that happened before Earth even formed. Take the Crab Nebula, for example. Its swirling filaments aren't just a beautiful light show. They're the shattered remains of a star that exploded in 1054, recorded by astronomers across the world. Today, we can study those same expanding gases to measure the exact energy of that blast, trace the elements it forged, even spot the spinning neutron star it left behind. It's like carbon dating a dinosaur bone, but instead of fossils, we're decoding the aftermath of a stellar death that's nearly 1,000 years old. But the real magic happens when we look beyond our cosmic backyard. Some white dwarfs we observe today are the cooled remnants of stars that died when the universe was just a fraction of its current age. Their atmospheres, often polluted with traces of silicon, oxygen, and iron, act like cosmic crime scenes. These elements shouldn't float atop a white dwarf's dense surface unless the star recently devoured a rocky planet. By analyzing these chemical signatures, astronomers can piece together what kinds of worlds orbited these stars billions of years ago, long before our solar system existed. It's as if each white dwarf carries a tombstone inscription. Here lies a star that once hosted planets. Then there are the grandest relics, supernova remnants like Cassiopeia A, whose shockwaves still ripple through space 350 years after the explosion. By mapping the distribution of elements like titanium and chromium in its debris, we've discovered that the original star didn't just explode, it sloughed off layers in violent eruptions before its final collapse. These aren't just snapshots of death, they're slow-motion videos of a star's last chaotic acts. Perhaps the most astonishing discoveries come from metal-poor stars in the Milky Way's halo. These ancient survivors, born from the ashes of the universe's first supernova, carry the chemical imprints of their ancestors' deaths. Their atmospheres contain bizarrely low amounts of heavy elements, suggesting the earliest stars died differently, perhaps in pair-instability, supernova so powerful they left no remnants at all. Studying them is like finding cave paintings from the dawn of time, revealing how the first generations of stars shaped the chemistry of everything that followed. What's remarkable is how these cosmic autopsies keep rewriting our textbooks. A single unusual white dwarf might hint at a previously unknown way stars can die. A supernova remnant with oddly distributed elements could force us to rethink how shockwaves propagate through space. Even the absence of evidence tells a story. Regions with too few neutron stars might be graveyards where black holes formed silently, without the usual fireworks. Every stellar ghost, whether it screams or whispers, adds another piece to the puzzle of how stars live, die, and ultimately make the universe we call home. The universe should be teeming with life, with hundreds of billions of stars in our galaxy alone, many older than our sun. The cosmic silence is deafening. This is the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial civilizations and our complete lack of evidence for them. One chilling explanation lies in the very stars that make life possible. Their violent deaths might be the universe's ultimate reset button, wiping out civilizations before they ever get the chance to call out into the void. Consider the sheer destructive power of nearby supernova. When a massive star explodes just a few dozen light-years away, it bathes surrounding space in lethal radiation. X-rays, gamma rays, and cosmic rays intense enough to strip planetary atmospheres and irradiate surfaces. Earth's fossil record shows potential evidence of such events, sudden mass extinctions that coincide with periods of increased cosmic radiation. Now imagine a galaxy where these explosions happen frequently. Just one supernova every few million years within 100 light-years could create a deadly rhythm, snuffing out emerging life forms like a cosmic game of whack-aim, all before they develop spacefaring technology. But supernova aren't the only threat. Gamma-ray bursts hyper-focused beams of energy from collapsing hypergiant stars or merging neutron stars are even more apocalyptic. A single GRB pointed at Earth from thousands of light-years away could deliver the energy equivalent of a nuclear bomb per square kilometer across half the planet's surface. The ozone layer would vanish, ultraviolet radiation would scorch ecosystems, and global temperatures would plummet. Now scale that up. In galaxies with higher star formation rates, like the early universe or modern starburst galaxies, GRBs might occur often enough to sterilize entire regions for billions of years. This leads to a haunting idea. What if the universe isn't silent because life is rare, but because the cosmos is fundamentally hostile to its survival? Stars create the elements necessary for life, but their deaths might ensure that life rarely progresses beyond microbial stages. The Milky Way's quieter outer regions, where stellar explosions are less frequent, could be rare safe zones where civilizations like ours occasionally slip through the cracks. Even then, the clock is ticking. Our solar system orbits within a galactic danger zone where a nearby supernova could still strike, with candidates like Betelgeuse looming as potential time bombs. Yet there's a flip side to this grim scenario. If civilizations do survive these filters, they might emerge wiser and more cautious. Imagine a species that endures multiple near-extinction events from stellar cataclysms. Their technology would likely prioritize early warning systems, radiation shielding, or even migration strategies to avoid cosmic threats. Some theorists suggest advanced civilizations might deliberately stay silent, hiding from potential dangers we can't yet perceive. The silence we interpret as emptiness could instead be a universe full of survivors holding their breath. The unsettling truth is that stellar death doesn't just shape the cosmos chemically, it might dictate its biological trajectory. The same explosions that forge the iron in our blood and the calcium in our bones could be the very reason we find ourselves alone in the darkness, listening for voices that were never given the chance to speak. Whether the universe is truly barren or simply playing a longer, more brutal game of survival remains one of the greatest mysteries written in the ashes of dead stars. Every atom in your body tells a story of cosmic destruction and rebirth. The oxygen you breathe, the iron in your blood, even the calcium in your bones, they weren't forged in the peaceful fires of living stars, but in the violent deaths of their ancestors. When a massive star explodes as a supernova, temperatures reach billions of degrees, creating conditions so extreme they force atoms together into heavier elements like gold, uranium, and iodine. These newly minted elements are then blasted into space, riding shockwaves that seed nearby gas clouds with the raw materials for new stars, planets, and eventually, life. But it's not just the explosive deaths that build the universe's chemistry. Even stars that fade quietly play their part. Take a humble sun-like star, slowly shedding its outer layers as a planetary nebula. That glowing halo isn't just a farewell, it's a delivery system. The star's spent fuel, rich in carbon and nitrogen, drifts into the cosmos. Over time, these elements mix with hydrogen and helium in interstellar space, becoming part of the next generation of stars. Our Sun and Earth likely formed from a cloud that contained ashes of countless dead stars, some that screamed, some that whispered. This cosmic recycling turns stellar deaths into stellar nurseries. The famous pillars of creation in the Eagle Nebula, those towering columns where new stars are born, are sculpted by the radiation of nearby massive stars that will one day explode, continuing the cycle. Even our solar system bears fingerprints of this process. Meteorites older than Earth contain microscopic grains of stardust, tiny time capsules from supernova that predate the Sun itself. What's truly staggering is the timescale. The iron in your blood could have been forged in a supernova that detonated 5 billion years ago, drifted through space for eons, then found itself part of a collapsing gas cloud that birthed our solar system. That same atom might have been inside a dinosaur's muscle, a prehistoric fern, and now you. The universe doesn't waste anything. Every stellar death, whether cataclysmic or quiet, is a down payment on future possibilities. Yet there's a beautiful irony here. The same explosions that could sterilize planets with radiation also provide the ingredients for life. A supernova too close would be apocalyptic, but one at just the right distance enriches nearby clouds with life's building blocks. It's as if the universe operates on a knife's edge, too little stellar death, and there's no chemistry for life, too much, and life gets snuffed out before it begins. This delicate balance raises profound questions. If supernovae are essential for life, does that mean galaxies with fewer massive stars, and thus fewer explosions, are less likely to harbor complex life? Or does the slower, steadier element production from smaller stars offer a safer path? We don't know yet, but every time we study the aftermath of a supernova or the composition of a white dwarf, we're piecing together the recipe that turned stardust into consciousness. So when you look at the night sky, remember, those stars aren't just distant lights. They're future creators and destroyers, destined to seed the cosmos with the elements of life, even if that life won't arise for billions of years. Their deaths are written into your DNA, a reminder that in the grand story of the universe, endings are often just beginnings in disguise. Simulating the death of a star isn't just about running equations, it's about recreating cosmic violence inside a supercomputer. Picture a machine crunching numbers so fast, it can model the final milliseconds of a supernova in exquisite detail, tracking shock waves, neutrinos, and elemental formation all at once. These digital laboratories let scientists dissect stellar deaths frame by frame, revealing secrets no telescope could ever capture. Take the infamous Chandrasekhar limit, the critical mass where a white dwarf tips from stability to catastrophe. For decades, theorists debated exactly how this collapse unfolds, but with modern simulations, we've watched it happen in silico, carbon igniting like a bomb, flames tearing through the star at thousands of miles per second, and the entire object vanishing into a fireball brighter than a billion suns. What's astonishing isn't just the scale of these simulations, it's their precision. When researchers modeled the death of a massive star recently, they discovered turbulence in the collapsing core acts like a cosmic air fryer, churning the star's insides into bizarre elemental soups. These turbulent eddies, invisible to observations, explain why supernovae sometimes fizzle, or why certain elements like gold end up clustered in strange pockets of debris. Without simulations, we'd never know that a star's final moments are less like a smooth explosion and more like a blender set to cosmic apocalypse. White dwarfs get the same high-tech treatment. Scientists can now simulate how these stellar embers cool over trillions of years, predicting when and if they'll crystallize into diamond-like spheres. Some models even suggest dark matter particles trapped inside could subtly alter their glow, creating hypothetical dark stars hidden in plain sight. And when two white dwarfs collide, simulations show they might not always explode as expected. Sometimes they merge into a zombie star, reigniting fusion like a cosmic phoenix. The real magic happens when simulations collide with reality. In 2017, when LIGO detected gravitational waves from colliding neutron stars, supercomputer models had already predicted the event's light signature. Telescopes swiveled to the right patch of sky within hours, capturing the glow of freshly forged gold and platinum, just as the simulations said they would. It was a triumph of digital stargazing, proving we can now not only witness stellar deaths but anticipate them. Yet for all their power, these simulations humbly remind us how much we still don't know. Some supernova models stubbornly refuse to explode unless programmers tweak hypothetical physics. Others hint that magnetic fields or rapid rotation might be the hidden keys to unlocking why some stars die with a whisper and others scream across the cosmos. Every unanswered question is a breadcrumb trail leading to deeper mysteries, proof that even in the age of supercomputers, the universe keeps its most dramatic finales close to the vest. 5 billion years from now, our familiar yellow sun will begin its final act not with a bang, but with a slow, luminous unraveling. Having burned steadily for 12 billion years, its core will finally exhaust the hydrogen fuel that's powered it since birth. What happens next is a cosmic metamorphosis so gradual, so inevitable, it's already written in the laws of physics. The sun's outer layers will swell, its surface cooling to a ruddy glow as it inflates to 200 times its current size. Mercury and Venus, those inner worlds baked by solar heat for eons, will vanish into the sun's expanding atmosphere, their rocky bodies dissolving like sugar in tea. Earth's fate hangs in the balance. Our planet may escape full engulfment, but its surface will be scorched to a barren crisp, oceans boiled away, atmosphere stripped by the sun's fierce stellar winds. This red giant phase isn't just about expansion, it's a star's last gasp for stability. With hydrogen fusion waning, the sun's core will contract under gravity's pull, growing hotter until helium, the ash of its previous fusion, ignites in a desperate new reaction. For a brief cosmic moment, the sun will regain equilibrium, burning helium into carbon and oxygen. But this reprieve is short-lived. Unlike massive stars that forge heavier elements, our sun lacks the gravitational muscle to push fusion further. When the helium runs out, the core collapses one final time, while the outer layers drift away in a series of gentle pulses, like a tree shedding autumn leaves. What remains is where the true poetry lies. Those expelled layers won't just dissipate, they'll form a planetary nebula, a glowing halo of gas illuminated by the sun's exposed core. For tens of thousands of years, this nebula will glow with ethereal beauty, its intricate shapes sculpted by magnetic fields and dying stellar winds. The Ring Nebula and the Helix Nebula, those iconic cosmic eyes peering through telescopes, show us exactly what our solar system will become, a fleeting work of art visible across light years. At the center, the sun's core will settle into its afterlife as a white dwarf, a Earth-sized ember with half the sun's original mass packed into a sphere no bigger than our planet. Initially blazing at over 100,000 degrees, it will glow white-hot for billions of years, its light fueled not by fusion but by residual heat slowly leaking into the void. Unlike the violent deaths of massive stars, there'll be no supernova, no neutron star, no black hole, just a gradual dimming as the white dwarf cools toward oblivion. Given enough time, far longer than the current age of the universe, it may crystallize into a celestial diamond, cold and dark, adrift in an equally ancient cosmos. This quiet fate isn't unique. Over 90% of stars in the Milky Way, including virtually all sun-like stars, will follow this same path. Their white dwarf remnants will outlast galaxies, persisting even as the universe expands toward heat death. Yet in their silence lies a profound legacy. The carbon and oxygen forged in the sun's final phases will enrich the interstellar medium, mingling with future generations of stars and planets. The very atoms in Earth's rocks in our bodies may one day be recycled into new worlds, a whisper of our solar system echoing across eternity. So while massive stars die in spectacular supernova, their explosions visible across the cosmos, our sun's exit will be a subtler affair. No shockwaves, no gravitational ripples, just a glowing nebula that fades and a white dwarf that dims, its light guttering out like a candle in an endless night. It's a reminder that the universe celebrates both the loud and the quiet, the explosive and the gradual, and in that balance, even a whisper can shape the future. Our Milky Way offers a front-row seat to stellar deaths, but step outside our galaxy, and the cosmic graveyard becomes far more diverse. In the Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, supernova erupt 10 times more frequently than in our own. Over in Andromeda, our nearest spiral neighbor, aging stars shed their skins in silent planetary nebulae at nearly double the Milky Way's rate. These differences aren't random. They're cosmic fingerprints revealing how a galaxy's history, composition, and even its collisions shape the way its stars die. Take starburst galaxies like Messier 82, where stars form at a frenzied pace. Here, supernovae detonate like firecrackers in quick succession, some so bright they outshine their entire host galaxy. The reason: these regions are packed with short-lived massive stars, each destined to explode within a few million years. The Tarantula Nebula in the Large Magellanic Cloud is a perfect example, a stellar nursery so prolific it's produced multiple supernovae in just the past few centuries. Yet contrast this with elliptical galaxies, those ancient orbs of aging stars. Their quiet skies tell a different story: fewer explosions, more white dwarfs cooling slowly into oblivion. Without fresh gas to birth new stars, these galaxies have become retirement homes for stellar remnants, their most dramatic deaths long since past. What's truly fascinating are the outliers galaxies where stellar deaths defy expectations. In ultra-diffuse galaxies like Dragonfly 44, stars are so spread out that supernova might eject their debris into near-empty space, leaving no glowing remnants to study. Meanwhile, in metal-poor dwarf galaxies like Segway 1, stars die with unusual chemical signatures, their explosions lacking heavier elements because they formed before the universe was richly seeded with metals. These oddballs challenge our models, proving that stellar death isn't one size fits all. Technology lets us witness these events across cosmic time. When Hubble captured supernova rifts DAL in galaxy cluster MAX J 1149, astronomers observed the same explosion multiple times thanks to gravitational lensing bending light around intervening mass. This cosmic replay revealed how a supernova's light curve behaves in a galaxy far younger than our own. Similarly, surveys like the Zwicky Transient Facility scan thousands of galaxies nightly, catching stellar deaths in progress from hypernova in distant spirals to quiet white dwarf flickers in ancient ellipticals. Yet the grandest perspective comes from galaxy collisions. When the antennae galaxies merged, their violent dance triggered waves of star formation and subsequent supernova at rates unseen in isolated galaxies. Such events remind us that a galaxy's environment, not just its stars, dictates how they'll perish. Whether in the crowded core of a cluster or the lonely void between filaments, where a star dies shapes how it's remembered and what it leaves behind for the next generation of cosmic architects. Space might be a silent vacuum, but that doesn't mean stellar deaths happen quietly, not if you know how to listen. Scientists have found a way to translate the light, radiation, and gravitational waves from dying stars into sound, a process called sonification. Take the Crab Nebula, the remnants of a supernova observed in 1054. When astronomers converted its X-ray and optical data into audio, the result wasn't just noise, it was a haunting, rhythmic pulse, like a cosmic heartbeat echoing across 1,000 years. The vibrations of its spinning neutron star, once invisible, suddenly became something you could feel. This isn't just artistic interpretation, it's science with purpose. Our ears detect patterns our eyes might miss. For example, the steady chirp of colliding black holes, first detected by LIGO in 2015, sounds eerily like a slide whistle ascending in pitch. That rising tone isn't random, it's the exact audio signature of two black holes spiraling closer. their orbital speed increasing until the moment they merge. Translated into sound, gravitational waves reveal nuances in the data that graphs alone can't capture, helping scientists fine-tune models of these cataclysmic events. Then there are pulsars, those lighthouses of the cosmos. When researchers sonified the rapid pulses of the Vela pulsar, the result was a metallic, almost mechanical ticking, like a hyperactive cosmic clock. But slow that audio down and hidden complexities emerge, slight variations in rhythm that hint at quakes on the neutron star's surface or turbulence in its magnetosphere. These sounds aren't just eerie, they're clues, helping astronomers diagnose the health and structure of stellar corpses from light years away. Even the silent deaths of white dwarfs find a voice. In 2020, astronomers sonified the light curve of a distant supernova, stretching its brightness fluctuations across the audible spectrum. The initial explosion registered as a sharp crescendo, followed by a slow, mournful fade like a gong struck once, then left to hum into silence. That deceleration mirrors the supernova's expanding debris cloud, its light dimming as it cools and disperses. What looks like a smooth decline on a graph sounds like a star's final sigh. But the most unsettling sounds come from magnetars. When these ultramagnetic neutron stars experience starquakes, they release bursts of radiation that, when sonified, resemble something between a scream and static. One particularly violent flare from SGR 1900+14, detected in 1998, produced a series of rapid, staccato pulses like a machine gun firing into the void. That wasn't just data, it was the sound of space-time itself recoiling from a magnetic field strong enough to distort atoms. Sonification does more than make stellar deaths accessible, it redefines how we experience them. A supernova's light might take centuries to reach us, but its sound can bridge that gap instantly, connecting us to the cosmos in a way numbers alone never could. Whether it's the rhythmic ticking of a pulsar or the discordant shriek of a magnetar, these sounds remind us that the universe isn't just something we see. It's something we hear, too, a symphony of creation and destruction, playing on a loop across the ages. And sometimes, the most profound discoveries don't come from telescopes or equations, but from listening to the stars as they whisper or scream their goodbyes. Stellar remnants like the Crab Nebula aren't just cosmic gravestones, they're time capsules, preserving the final moments of a star's life in glowing detail. That iconic wispy structure we see today is the aftermath of a supernova observed in 1054, when a massive star collapsed and rebounded in a shockwave so powerful, it outshone the entire night sky for weeks. But here's what's astonishing. Nearly 1,000 years later, the nebula still pulses with energy, its filaments expanding at over 3 million miles per hour. At its heart spins the real ghost, a neutron star spinning 30 times per second, its magnetic field channeling radiation into beams that sweep across space like a lighthouse cutting through fog. These remnants aren't just passive scenery, they're cosmic factories forging new elements and sculpting the interstellar medium. The crab's filaments, for instance, glow not from starlight but from synchrotron radiation, electrons spiraling at near light speed around magnetic fields. This process creates eerie blue tendrils rich with ionized oxygen and sulfur, elements that will one day seed future stars and planets. Meanwhile, shockwaves from the original explosion continue plowing through surrounding gas, compressing it into dense knots that might eventually collapse into new stellar nurseries. It's stellar reincarnation in action, one star's death giving rise to the raw materials for its successors. Yet not all supernova remnants follow the same script. Compare the Crab to Cassiopeia A, a 300-year-old remnant whose debris forms a chaotic, bubble-like structure. Here, the explosion was asymmetrical. Some material hurtled outward faster than others, creating jagged spikes and voids in the expanding shell. Then there's the Ia Supernova remnant, whose delicate filaments resemble shattered glass frozen mid-explosion. These variations aren't random, they're forensic evidence. The shape of a remnant reveals whether the original star rotated rapidly, had a binary companion, or shed layers in violent pre-death eruptions. What's haunting is how temporary these spectacles are. Over tens of thousands of years, the remnants dissipate, their glow fading as the expanding gas thins and cools. The neutron stars or black holes at their centers may persist for eons, but the visible echoes of their birth, those radiant nebulae we photograph, are fleeting by cosmic standards. That makes every image of a supernova remnant a snapshot of a singular moment, the split second between a star's death and its eventual disappearance into the interstellar dark. Perhaps the most profound lesson lies in their impermanence. These glowing ghosts remind us that destruction and creation are two sides of the same cosmic coin. The same explosion that obliterates a star also builds the ingredients for planets, for life, for future stars to rise from the ashes. So when we gaze at the Crab Nebula's shimmering tendrils, we're not just seeing a corpse, we're witnessing a legacy, a star's final act rewritten into the next chapter of the universe. For all we've learned about how stars die, the cosmos still guards its deepest secrets like a vault. Take black holes, those cosmic vacuum cleaners where gravity wins so completely, not even light escapes. We can calculate their mass, measure their spin, even photograph their shadows, but what happens beyond the event horizon? The laws of physics as we know them break down at the singularity, a point of infinite density where space and time cease to have meaning. Some theories suggest matter gets stretched into quantum spaghetti, while others propose it emerges in some bizarre new form in a parallel universe. The truth. We're peering into the ultimate cosmic black box. Then there's the quark star conundrum, a hypothetical object so strange it makes neutron stars look ordinary. When massive stars collapse, conventional wisdom says they become either neutron stars or black holes. But what if there's a third option? Under unimaginable pressure, the neutrons themselves might break apart into their constituent quarks, creating an ultra-dense quark-gluon plasma star. A few candidates like XTJ 1739-285 have shown pulses so fast they might fit the profile, but the evidence remains tantalizingly inconclusive. Discovering one would rewrite our understanding of how matter behaves under extreme conditions. Even familiar stellar deaths hide riddles. Why do some supernovae explode asymmetrically, shooting their debris in one direction like cosmic shotgun blasts? How exactly do white dwarfs ignite when they cross the Chandrasekhar limit? Is it a smooth burn or a detonation? And perhaps most perplexing of all, what's the true nature of fast radio bursts? These millisecond-long cosmic radio signals might be linked to magnetar flares or neutron star collisions, but their precise origin remains one of astronomy's most electrifying puzzles. The most humbling realization, every answer we uncover reveals new questions. When gravitational wave detectors caught two neutron stars colliding in 2017, it wasn't just a triumph, it was a reminder of how much we don't know. The event produced more heavy elements than predicted, suggesting our models of extreme nuclear physics are incomplete. Similarly, when the James Webb Space Telescope recently spotted galaxies that looked too mature for the early universe, it threw a wrench into our timelines of stellar evolution and death. These aren't just academic curiosities, they're clues to the universe's grand operating system. Solving how quark stars form could reveal new states of matter impossible to recreate on Earth. Decoding black hole singularities might unlock secrets of quantum gravity. Even understanding why some stars die quietly while others scream could tell us why our cosmos looks the way it does. For every stellar ghost we've catalogued, there are countless others lurking in the dark, waiting to rewrite the rules. The universe's greatest lesson might be this: the more we learn about how stars die, the more we realize how much wonder remains. From the silent fade of white dwarfs to the universe-shaking screams of supernova, stellar deaths are as diverse as the stars themselves. These cosmic finales shape the universe, scattering the elements of life and warping space-time itself. Whether a whisper or a scream, every star's death tells a story, one that we're only beginning to understand. Think about the atoms in your body right now, the iron in your blood, the calcium in your bones. These weren't forged in the gentle fires of a living star. They were born in chaos, blasted into space by the violent deaths of massive stars that exploded billions of years ago. The oxygen you breathe, it might have drifted through a planetary nebula, the last gasp of a dying sun-like star. Even the gold in your jewelry was likely created in the collision of two neutron stars, a cataclysm so powerful it rippled the fabric of space-time. Every element heavier than helium is a relic of stellar death, a cosmic inheritance from the stars that came before us. But it's not just about chemistry. The way stars die shapes the very structure of the universe. Supernova shockwaves trigger the birth of new stars by compressing nearby gas clouds. Black holes, the silent remnants of the most massive stars, anchor galaxies with their gravity, their immense pull dictating the motion of billions of stars. Even the faint glow of white dwarfs, those faded embers of sun-like stars, helps astronomers map the history of our galaxy, their cooling curves acting like cosmic clocks that reveal the age of stellar populations. What's truly humbling is how much we still don't know. Why do some stars die in near silence while others tear themselves apart with enough force to outshine galaxies? How do magnetars, those ultramagnetic zombie stars, maintain fields strong enough to distort atoms from thousands of miles away? And what secrets lie beyond the event horizons of black holes, where the laws of physics as we know them break down? Every answer we uncover seems to lead to 10 new questions, a reminder that the universe is far stranger and more wonderful than we can imagine. So the next time you look up at the night sky, remember, those twinkling lights aren't just pretty decorations. They're cosmic storytellers, each one destined for an ending as unique as its life. Some will fade quietly into the dark, leaving behind only a cooling ember. Others will go out in a blaze of glory, their final act echoing across the cosmos. But all of them, whether they whisper or scream, will leave their mark on the universe, shaping the stars, planets, and even the life that comes after them. If you enjoyed this journey through stellar fates, don't forget to like, subscribe, and share your thoughts in the comments. What fascinates you most about how stars die? Is it the violent beauty of supernova, the eerie persistence of white dwarfs, or the mind-bending mystery of black holes? Let us know. We love hearing from fellow cosmic explorers. Until next time, keep looking up. The universe has countless more stories to tell, and we're just getting started.